Obviously, if you're doing an integral, right? If you're given an integral and you have no idea how to start it, right? They're not going to just lead you by the hand through it. They want you to, you know. So I don't know. I wasn't part of that conversation, but I would be very alarmed if they're telling you, yeah, sorry, you're on your own, you know, because that's not what they're supposed to. But at the same time, you know, it's Cal 2, so you have to have some idea of what's going on. I don't know. I mean, overall grades in the class, I think a lot of you are still in a position where even if you didn't pass this test, you're still in a position to pass the class. So, yeah. Any questions or comments? I mean, what I'd like for you to do is I'd like for you to make corrections on the test and turn that in for a quiz grade, all right? So if you got a perfect score, then you're going to turn, like if you got the 105, you can just turn in a piece of paper with your name on it and just say, you know, here, right? I had no corrections. If you got a 98, right, you can just, again, make that quick correction. You're going to get 100 on the quiz. But if you're on this end, you got a lot of work to do, right, to get that quiz grade. So let's make that due a week from today, all right? And the whole idea behind that, here, if you want to get your test, the whole idea behind that is just to make sure that you have a chance to go back through and see what went wrong. Let's see. All right, can we move on? Are there any other comments or questions? So what happens in this class now is that we move into chapter 7, right? And chapter 7 is going to be very visual. It's not going to be like the techniques of integration. A lot of people do better with chapter 7, but at the same time I have students that do worse on chapter 7. You know, it just depends on you. But I would say, like on average, the next set of material, chapter 7, goes better than what we just tested on for most people. So that's kind of encouraging. But chapter 8 is where things get really, really rough. And so the next test you want to do well on, and that test is scheduled for November 15th. The drop date is November 16th, and that's intentional. That's to make sure that you have 3 exam grades before you make any decision about dropping the class, all right? I'll give you that test on the 15th. I'll grade it that night. The next day you'll know whether or not you should stay in or jump out. I mean, some of you are like, I need to have an A no matter what, so if I can't get an A, I'm gonna drop. Some of you are like, I just need a C and I'll be okay. So, you know, everyone's kind of in a different place when it comes to what grade they want in here. So that's the plan, and then we get to then we move into the next test, which will be the final. So we have exam 3 and then the final. Okay, here we go. So I'm going to leave this up today, and I don't want to dim the lights, but y'all let me know if y'all have any problems seeing what I'm doing up here today. So chapter 7, we're going to do some applications of integration. So we're going to try and apply these antiderivatives to something. And we already saw that the antiderivative allows us to find areas under curves, right? Areas under curves. So we're now going to continue with that idea. 7.1. Oh, no, that's Cal 3, sorry. Okay, so now what we're going to talk about are areas between curves. And these notes, again, are all online, but I added this to the notes recently, so this is not online, but it's not something I think you necessarily need to write down. I just wanted to have it written up here for you. It's to remind us what we mean when we say that we are looking at a function. Because right now, if I say, hey, if it's a function, you know, it passes the vertical line test, blah, 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 most of us are like, yeah, sure, I understand what you're saying. But we need to be more specific. We need to be more specific now. When we talk about functions, we have to say whether or not we're talking about a function of x or a function of y. Those are 2 different things. So when we are given an equation containing 2 variables, all right, so let me give you an example over here. If I give you this equation, let's go real simple. 2x plus 4y equals 8. That's an equation containing two variables, right? All right, so this says if you're given that, if the graph of that relationship passes the vertical line test, then we will say that, oh, I'm using the wrong mouse. We will say that if it passed the vertical line test, then we will say that if it passed the vertical line test and we can solve the equation for y, then we will say that y is a function of x. So if you can take this and solve it for y, let's do that real quick. Solve for y. I'm going to subtract 2x, add 8, right, like that. Divide both sides by 4. So divide by 4, I get negative a half plus 2, right? I can solve this equation for y. And because I can solve it for y, I can then replace y with f of x, and then we would say this is a function of x. And if I graph that, it's a line, right? It's a line. And the line would pass the vertical line test. Actually, it would have a negative slope. It'd be like this, but it would pass the vertical line test. All this is saying is that goes for any equation, right? Any equation, if we can solve it for y, and the graph passes the vertical line test, then we will say that y is a function of x. Are we good? Yes? That's not new. That's what you should expect. But we have a second condition, or second scenario, and that is, what if we take this equation and instead of solving for y, we solve for x, right? Solve for x instead. That's not something you normally do, but we could do, right? We solve it for x, we get 2x equals negative 4y plus 8, and now divide by 2, you get that, right? And so now x is a function of y, right? Back here when we said that y is a function of x, what we meant was that if you give me an x, I can then tell you what y is. Here, if you give me a y, I can tell you what x is, right? So we would say here that replace this with f of what? Y equals negative 2y plus 4. And here we would say that we are dealing with a function of y, not a function of x. If we graph it, it's the same line if we graph it, but instead of passing the vertical line test over here, it would have to pass the horizontal line test. So that's what this is saying. Is that if you have this relationship between x and y, and you can solve for x, not y, then your x will then be a function of y. It'll look like this, and it must pass the horizontal line test. So looking at that red graph right there, look at this red graph. By the way, that's not this, right? This is just to give you like a different example. For this red graph, could you say that this is a function of x? Does this graph represent a function of x? No, because it fails the vertical line test, right? But is it a function of y? Yes, right? Okay, so that's important for what we're about to do. So what we're doing here in this section, that was just a preliminary concept. We are trying to find the areas between two curves. We already know how to find the area underneath one curve, right? But how about between two curves? So we're going to have two different methods for doing this. The first method is going to be where we're going to use vertical rectangles. You'll see in the picture. We're going to use vertical rectangles to find these areas. And this is what we do when we are dealing with functions of x. Okay? Whenever we have functions of x, we're going to use this method. So if you give me two curves, right? I'm going to have the illustration here, but I want to put it up here first. If you give me some function f and some other function g, let's say we start and stop them at the same endpoints, a and b. We're interested in the area between those two curves, right? That's what we're interested in. And we agree with my picture, my drawing here, that the f and the g are both functions of x, because they both pass the vertical line test, right? So I'm saying that when we see this, we're going to use this method, right? The method is, and we're going to develop the formula. I hope it's going to be easy to see. It's a little bit bigger. Is that okay? Do I need to dim the lights, or is this okay? All right with it? Okay. I need a pointer. I wish. Let's use this. All right, so here's the picture I just drew over here, right? We have some function, the blue one that's on top, right? The blue one's on top. The red one is on the bottom. And I want to know the area of this region. So what I'm going to do is I'm going to use vertical rectangles. So imagine, remember when we were doing areas under a curve, we did a bunch of rectangles, right? So I just imagine some arbitrary rectangle in here. Here it is. Let's go look at that over here. And let's see if we can find a formula for the area of that single rectangle. If we can find a formula for that area, then we can use the integral to add up all those areas, right? That's what the integral does. It adds them all up. So with this rectangle, we need to look at, well, here's the x-axis, right? I need to know the area of this. So let's talk about how wide it is first. The width of it is the dx. That's that little infinitesimal width, just like it was with areas, right? With what we did before. So the width is dx. The question is, how tall is it, right, from here to here? And for this, we have to realize that from the ground, or from the x-axis all the way to the top, right, that's f. That's how tall f is. And then from here to here is g, right? So that distance is that distance, that's g. And then from here all the way up is f. So wouldn't the distance from the bottom to the top just be the difference of those two? Just take the f and subtract the g, right? Take the f, subtract that g, and that's that difference. So that's how tall it is. So this is the height, right? The width is dx, so here's the area of that one slice. It's the height times the width. And then I just stick that in the integral. There's the height, there's the width, and then add them up. Get it? And that's all it is. Okay, so that's our formula, all right? That's our formula. So we are going to do an example before we get to that. All right, so here is an example, and I'm not going to show you the picture yet. So sketch the region bounded by these two curves. So this is a point in the class where you want to start bringing your graphing calculators if you have them. They're not required in this class, but I know a lot of you own them, and it's time to learn how to use them. All right, so we're gonna be using them. I'm gonna show you. How many of you have a graphing calculator? How many of you do not have a graphing calculator? Okay, if you do not, go to the tutoring lab. Okay, room 308. Let me make sure. JH 308. And this goes for anybody who does not have a Texas Instruments graphing calculator. TI, you can have like an 84, TI 85, TI 89, whatever. If you don't, go to JH 308, and there's a little bit of paperwork you have to fill out, and you can check out a calculator for the rest of the semester. Okay, it's not required, but if you really want to be able to follow along and use it as a guide to help you during a test, go check it out. All right? Yes?
Are there any charges to it?
Nope, it's free. You have to return it though. Yeah, that you have to return. Okay, so I'm going to use, today you'll see me use this. If you were watching before class, I just downloaded this. This is called an emulator. So this is the TI-84, and I can just kind of click buttons here, and you'll see what the screen, shows, and we'll kind of do that. Unfortunately, you can't use that on a test, or else I just tell you to use this. But yeah. All right. So we got to sketch the region bounded by these. All right. So let's first just write down the two. What we got? Sketch the region bounded by y equals 2 minus x squared and y equals negative x, right? Okay. We want to sketch the region that's bounded by those two curves, then find the area of that region. So you've got to know what these look like, right? You've got to know how to graph these. And that's going to depend on your background, how comfortable you are with graphing this. And if you can't graph it out of your head, then you're going to have to use some graphing utility, right? So I'm going to do it out of my head first, and then we'll go to the calculator and I'll type it in and we'll graph it. All right, so here's what I know. Because I took college algebra, I know what y equals negative x looks like. That's a line. It has a slope of -1 and a y-intercept of 0. So I know that this just looks like a diagonal like this. Now I'm going to just use a color here to help us. I'm going to do this one in blue. Okay. So that's this one. This is y equals negative x. I'm just trying to get like a rough idea of what this looks like at this point. Now, this one, I'll point it out in a second. This one, y equals 2 minus x squared. Well, you should know what x squared looks like, right? Parabola. You should know what negative 2x squared looks like. Negative x squared. That's flipping it over, right? And then this 2 does what? Moves it up. So this is really like negative x squared plus 2. So it's just a parabola that opens down that's been moved up 2. So it looks, I don't know, up, let's say that's 1, let's say that's 2. It does something like this. Comes down and does something like that. All right, that's y equals 2 minus x squared. Now, I'm trying to sketch this and find the region bounded by the 2. Do you see that if I extend this line a little bit more, do you see that it encloses a region? Does everyone see the region? Okay, the region is here. And what we want to know is what is the area of that, right? What is the area of that region? All right, I'm not going to do the graphing calculator yet. Let's just stick with this, all right? All right, so to do this, here's what I need to do. I need to figure out, are these both functions of x? Do they both pass the vertical line test? Yes? They both pass the vertical line test. So I know that what I'm going to do is I'm going to wind up putting in a rectangle like this, right? And if I do a vertical rectangle over here, I know that the top of that rectangle, right? The top of that rectangle is always the red one, the red function. And the bottom of that rectangle is always the blue function, isn't it? And so if I want to know how tall this rectangle will be, it will always be the top one minus the bottom one, right? Top minus bottom. Now, I need to write these as functions of x. So this was already solved for y, right? So I can put f of x equals 2 minus x squared. And this bottom one, let's change this. Come on. Let's change this to g of x equals negative x. So I have a function of x up top. I have a function of x on the bottom, f and g, right? According to the formula, right, we're supposed to take the f and subtract the g. Whichever one was on top, subtract the one on the bottom. Got too many freaking caps here. All right, so I'm going to take the f and subtract the g, and then the width of this thing is always going to be dx, right? In other words, if you want to look at another way, we're taking the top one and subtracting the bottom one, right? That's really what's happening here. We're taking the top function, subtracting the bottom one. Okay, the top function for us is what? 2 minus x squared. So I'm going to take 2 minus x squared and subtract from that what? The bottom, which is negative x. 2 minus x squared and then minus x. So that just becomes 2 minus x squared plus x, right? That's what this is. All right, we good? So here's what I know so far, all right? So far, I know that I'm going to do this integral. I know it's the top minus the bottom, which we just found is 2 minus x squared plus x. That's the height times the width, right? Height times the width. What am I still lacking here? What do I still not know? Yeah, the endpoints, right? These limits of integration. Where do I start? Where do I stop? Well, that's going to require a little bit of thinking, isn't it? A little bit of work, because I need to know where this region starts, right? I need to know what x value that starts at. Actually, let's call it a, right? And then I need to know where they hit each other here at the end. And that right there will be my B. Do you all see that? I need to find those 2 points. They're not given to me. They're not explicitly written out, are they? So how are we going to find those 2 points? Well, it's where the two curves hit each other, right? And two curves hit each other when they are equal to each other, right? So I just need to set these two functions equal to one another and solve that equation, right? So I want to know when the red hits the blue. That means I want to know when the red is equal to the blue. So I'm going to do that here because I'm limited with space today. Finding the intersection. So I'm going to put here the intersection of these two curves. I set the 2 minus x squared equal to negative x. So I'm setting the f function equal to the g function. And now I solve that. What type of equation is that? Quadratic, right? How do you solve quadratic equations? Get everything to one side. I'm going to move everything to the right side. Right? That's just me moving everything to the right. Then either factor or if factoring fails, what could you use here? The way? You could complete the square, yep. Or you could use a quadratic formula. Okay, so you've got all those tools at your disposal. Hopefully it factors. Does it factor? Yes, it factors. X minus 2, x plus 1. Right, so we factor that quadratic. We set each factor equal to 0. We get two solutions, negative 1 and positive 2. Bless you. Bless you. So that means that this A was negative 1 and this B was 2. And that gives me my limits of integration, negative 1 to 2. And that's it. We just got to calculate whatever that integral is now. Any questions? Draw the graphs, figure out where the region is, figure out that these are both functions of x, so we're using vertical rectangles, came up with a formula for the rectangle, right? Put that formula in here, had to figure out the limits of integration, so we set the two functions equal to each other, got the 2 points. Now we actually have to grind this out, right? So here we go, let's do this. So for this, how do we do this? Fundamental theorem of calculus, right? So we do the antiderivative of each one of these, right? We can do them one by one because there's addition and subtraction. So 2x minus 1/3 x cubed plus 1/2 x squared. Then that evaluation bar, negative 1 to 2. So antiderivative each of the three. What gets plugged in first? 2 goes in first, and then after that we will subtract what we get when we plug in negative 1. So let's plug 2 into this. It's going to be kind of nasty, but let's see. 2 times 2 is 4. See, 2 cubed is 8. 8 times 1/3, that's minus 8/3. And then 2 squared is 4. 4 divided by 2 is 2, so we get plus 2. Then when we plug in negative 1 goes in there, we get negative 2. Negative 1 goes here, negative 1 cubed is negative 1, and then times the negative 1/3 is positive 1/3 or plus 1/3. And then negative 1, when we square it, we get 1, and then times a half is a half, so plus a half. And this is just a number, right? Just have to figure out what this number is. So this is, let me just put these together. That's 6 minus 8/3. And then over here, let's distribute the negative through. So plus 2 minus 1/3 minus a half. Trying to avoid using my calculator if possible. I think I might be able to avoid the calculator. Can you put these two together? What are those two together? Minus 9/3, but 9/3 is 3, so minus 3. So this is going to be 6 take away 3, that's these two, plus 2, and then minus a half. 6 take away 3 is 3, 3 plus 2 is 5, so 5 take away a half. Now get your common denominator. 4.5, or I'm just going to put 9 halves. 4.5 would be fine. 9 halves. That's the area between those two curves. All right, good? All right, let's go bring up this little graphing thing. I hope you can see that. I can't make that bigger. That's the biggest it can be, all right? So I'm going to turn this on, and then I'm going to go to y equals, And then here I'm going to type in the first one, which was 2 minus x squared. 2 minus x squared. Hit enter. Then I'm going to do the other one, which was just negative x. So I put the negative in front of x. And then I hit graph. There they are. Okay. And you can zoom here. You can zoom in if you click the zoom button and just go zoom in, which is number 2. And then what you can do is you can use the up and down arrows to kind of tell the computer where you want to zoom into. So I'm picking kind of like the focal point, and then once you pick that point, hit enter, and it's going to zoom in. And it has like a default setting that you can't really change, so there it is. You can also do zooming. If you want to go back to the regular zoom, hit zoom, and then there's a thing here that says zoom Z standard. That's like the standard window. So that's number 6. If you hit number 6, it'll take you back to normal zoom. You can also adjust the window instead. If you hit window, what this does is it allows you to control where it says X min and X max. It allows you to control your X left X and right X. And then where it says Y min and Y max, that controls your Y bottom value and top value. So I know from my answer, I'm only interested between -1 and 2 on X, right? -1 and 2. So I'm going to graph, I'm going to change this window. I'm going to change my X to -2 and the left endpoint to -2. See how I do this. Clear that. I'm going to put -2. And then on my Y max, I'm going to put, what does it go to? It goes to 2. I'm going to go to 3. And then I'm just going to hit graph and see what I get. All right. I'm just kind of showing you some of the little things here. You may know this already. I'm going to adjust that window a little bit more. I'm going to do my Y max. Let's do my Y min. Let's turn that to -5. I'm just kind of playing with numbers here. And then I'm going to do, for Y max, I'm going to do 5. Graph, see if that's any better. Not bad. Okay. Ready for the next one? Next problem? Oh, and yeah, that picture over here, that's just what we did, right? We found the area of that. The area of that was 9 halves. All right, sketch the region bounded by those 2 curves. Oh, wait, sorry, I said 2 curves. It says sketch the region bounded by blah, 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 then find the area of the region. They gave us 3 different things, didn't they, instead of 2? Okay, let's see how that changes things. So y equals square root of x. Y equals x minus 2, and y equals 0. All right, let's go with our picture over here. Okay, square root of x. Everyone here knows what the square root of x is, right? Or what the graph of it looks like. That's square root of x. Roughly speaking. Okay, y equals x minus 2. What is this? It's a line, has a slope of 1 and a y-intercept of -2. So I go down 2, 1, 2, and I draw a line, has a slope of 1. Something like that, right? So down 2, draw a line, slope of 1, roughly looks like this, right? I'm going to go get another color. It's right across the hall. Y equals 0. Y equals 0 is what? Y. It's a horizontal line. It's actually the x-axis, isn't it? Y equals 0 is the x-axis. All right. Do you see the region bounded by all of those? Yes? It's right here. Are all three of those functions of x? In other words, are all three of these, can you solve them for y? Yes. Well, they're already solved for y, right? So yes, they're functions of x. You could say, let's see. So they're all functions of x, yes? Let's see where a rectangle would be. Like, remember, we're going to put rectangles, vertical rectangles in here. We're going to run into a problem. Let's see if you can identify it. If I draw my rectangle here, okay, if I draw that rectangle, and I want to know the area of that, what curve is on top? The blue one's on top, right? The blue one's on top, and which one is on the bottom? The green one, right? The green one. But that's not always the case, is it? Remember, we've got to have rectangles in the entire region. Do you all see that if I do my rectangle over here, right, that the top one is what? Blue, and the bottom one is red. And that's not, it's not the same, is it? So the way that you look about, the way that I like to look at the integral is that we're going to be adding up all these rectangles, right? We're going to be adding up all these rectangles within here. Starting at our left end point A, and then we're going to just move our rectangles across. Just add them up all the way across, right? And what we need is when we get to the end point B, we need for the formula we're using to never change, right? Top minus bottom has to be the same the whole time. But see, what happens is as we move across here with our rectangles, right, we've got blue on top, green on the bottom until I get to there, and then it's blue on top, red on the bottom. So it switches. So how do I resolve that? Split into two integrals. Exactly. Find this point, right, and we're going to break it into two different integrals. We're going to find this point, we're going to split it here, and then we'll find this area, we'll call it area 1, and then this one we'll find area 2. And then the true area that we're looking for will just be the sum of those two areas. Does that make sense to you? But the reason we're doing it is because the formula changes, right? Switches. And right here at this point, we have a different formula. So this is for area 1. Let's do these one at a time. I need to label these, all right? The blue is on top for both of these, right? The blue is on top. Let's call the blue one f of x. F of x is root x. All right, now this one right here is on the bottom for some of the time, and then the green one's on the bottom for other parts of the time. So I'm going to call this one g of x is x minus 2, and the green one, I'm going to call that one